Hi again, and this is Dr. Fateh and a series exploring the secrets of nature. Today, we're doing the second part of holography or wavefront reconstruction and recording process. This is part two, and it will be the theoretical explanation of how the processes of making and viewing holograms works. I hope you have enjoyed the first part of this presentation. In this theoretical explanation, we'll formulate in mathematical, of course, in a friendly way, mathematical way of the beams, and hopefully we'll be able to show you what each of these equations would mean. We will introduce three beams: the object beam, the reference beam, and then we add them up together to generate the total beam and look at the intensity distribution to which the holographic film, or photographic film rather, is exposed pixel by pixel. Then upon processing the film and placing it in a holder, it will be illuminated by a reconstruction beam, which in turn generates the reconstructed beams or reconstructed wavefronts, which actually has three parts to it: a DC part, or noise, or distorted information, or useless information; a second part which has got the principal image, and I'll explain what principal means as compared to real image. It's different from the word real or virtual. And contrast to principal image, we'll have a conjugate image, which is a mathematical complex conjugate of that image. We will discuss the interpretation of all of these. And then, of course, I hope you have seen part one. So let's introduce the main three beams in order. First, we have to agree on a coordinate system. We will use the z-axis as the direction of the travel of the beam as shown, and x and y as the direction of the electric and magnetic fields of the light. We also assume that the wave is traveling mostly in the z direction, and definitely we consider paraxial ray approximation, which means it's not too much diversion from the z-axis. So putting it all together, a complex wave emanating from this object here, or this picture here, or this person here, is explained in general as shown in this equation. We have got an intensity of the object beam, which is a function, and it's a vector. I'm showing it vectorially as a function of x, y, and z, which really consists of, at each plane that is perpendicular to the z-axis, is shown by an amplitude E0 of x and y plus a phase difference at x and y. These are phi and theta. And then I've factored out the traveling wave part of it, which is always there, and it indicates that the wave is traveling in direction, and it's a periodic in time, and it's expressed mathematically by e to the j omega t and e to the minus j gamma z, where omega t means periodicity in time and gamma z means periodicity in the z direction. Now from now on, we could always omit this factor, assuming that the wave is traveling in the z direction, and its period is given by 2 pi over the period of over its period, or 2 pi times its frequency, and also the gamma is 2 pi over the wavelength lambda. So right now, as you put your eyes here, look at the wavefront, you can see a three-dimensional information, which means all the amplitude and phase information emanating from this object. Now you place the hologram in at location z equals 0. Therefore, your purpose is to record all of the phase and amplitude information emanating from the object on this z plane. Now note that since you do not have any lenses, the wavefront hitting the plate is nothing resembling the original object because you're not using any focusing images. It's just like distortions on the phase of a wavefront traveling through the holographic plate. So as it is right now, really, there is no visible image. Of course, if you put your eyes here somewhere, you can see the uh, object because your eye lenses focus the image onto your uh, optical nerves. Now, I introduced the second beam, which is coming from, as you saw in part one, from the same source. Therefore, it is coherent with the light that illuminates the object. We call that reference beam. And let's assume that it's only a plane wave, which is in simplest form. A plane wave traveling at an angle with respect to xz and yz planes. And this angle can be calculated given or these two factors, or we could do it vice versa. Now I didn't bother to calculate here. It's but in generic form, that reference wave vector r as a function of x, y, z is given again by an amplitude at any location r0 of xy plus a phase. Now this phase is not very complicated. It's simple. It's just linear in x and y direction. So e to the j something times x plus something times y, and those you have those factors I've called omega x and omega y, and these determine the angle at which it goes. So that we'll leave it as an exercise to calculate what angles they make. Now this is the traveling wave factor, the last part, e to the j omega t and gamma z. I have marked them as omega prime and gamma prime for the purpose of generality, but in reality, the omega prime should be equal to omega. Otherwise, the pattern would not be stationary and we cannot record by time exposure of the film. And similarly, gamma prime should be equal to gamma. This is for the stability of the patterns. Again, we can ignore this factor, traveling wave factor, anyway. Now we add up both of those reference and object beams together because that's what is happening. So point by point, the field intensity, the electric field intensity, or the amplitude of the object beam E and the reference beam I add up together. Now, the thing is that the photographic film is sensitive to the power at each point. That is, we call intensity of light. It is not, it does not record the amplitude. It's in a way like a square law detector. For those who are electrical engineers, this acts like a diode or a square law device. So mathematically, it means the intensity at location z equals 0 as a function of x and y of the total field is simply the addition of the two field vectors to the power 2. Or at least it's proportional to that. Some people add a factor of half and whatever. Now, this can be written mathematically in terms of the total field times its complex conjugate. Now remember, let's recall complex conjugation means simply you invert the phase of a signal. So complex conjugate, if you recall it, the temporal signals or time dependent signals, a complex conjugate of time signal is you convert all of the time phases and inverse it. Now, carry out the multiplication. So you have got E times its conjugate. You've got a reference beam vector times its conjugate. Forget about those, but these two other factors are very clear. Now, if I write these in terms, separate out these and carry out the multiplication and write it in terms of R0, what you have here, the first term is something very funny. On the second term, you have the original electric field original amplitude, object beam, that once emanated from the object, multiplied by the phase function of the reference beam, that is, in other words, angled in the same direction, and of course amplified by R0. And the third term is the same value, except you have the the original but complex conjugated, which means all the phases are inverted. Now these three parts make up the actual signals that will later will be emanating from the hologram during viewing. Now when you make the hologram, you simply expose the film for a period tau to this light energy, and you assume it is linear. By the way, everything in its nature is, for small amounts, is linear. We call that piecewise linear. So we use a linear portion of the photographic film where exposure is linear, and this is misspelled here. And then later on, the transmission of the when you develop the film and put it back in there, the transmission of the film is somehow proportional to the intensity at each point if you're using the linear region. Remember, if you use nonlinear region, a lot of distortions happen, just like it does happen in temporal signals. Now the transmission as a function of x and y of the hologram, t, is now the integration during exposure time of the intensity. But it can be simply written as t times that intensity. You carry out the multiplication, and you have got onto those three terms. You come out with hologram containing a DC part, noise, or whatever I call that, which is these values. The meaning doesn't matter because the formula, I'm not going to deliberate on it because it's going to be useless. But these two terms are important. You've got the amplified version of the original signal, but multiplied by the phase of the, or by the complex conjugated of phase of the beam, of the reference beam, and conjugate of both of this. Now this carries the complex conjugate of the original object, and I'm calling it funny stuff because you'll see why it is funny. As I said before, call all of these factors here just like a gain or loss factor or amplification factor. Now we put the exposed hologram or processed hologram and back in its place, and let's view the reconstructed beam. We illuminate the object with yet another beam, which I call the reconstruction beam, traveling, could be at a different angle, but I've chosen here to travel in the same direction as the original reference beam, and I'm calling it beam C, complexly defined as this equation containing again an amplitude C0 and a phase j omega x x and j omega y y minus, which is, if you recall, it is exactly the same as the reference beam. It doesn't have to be, but this makes it easier to explain. And this is again the traveling factor at the end. Now I've called this gamma double prime and omega double prime, and I'm here saying that let it be equal to that. By the way, it doesn't have to be equal exactly to the original object beam. If wavelength is different, it simply leads to a sort of magnification of the lateral magnification of the object. But for now, let's just take it's equal. So if you want to play around with non-equality, it's simply you will get a magnification, not amplitude magnification, but lateral magnification. But if you ignore that for now, our reconstruction beam is given as a amplitude C0 times the function times the angular angle function e to the minus j omega xx and minus j omega yy. Excuse me. Uh, Now, this multiplies by the hologram transmission line, and whatever comes out is our reconstructed beam in the next slide. So once you eliminate the object with the reconstruction beam as shown here, then you do this multiplication, and the waveform D is generated, which is simply a product of the transmission of the hologram times the reconstruction beam on point-by-point basis. So you carry out the multiplication, and you get these terms, and this highlighted equation is the result of the illumination, and you will see it has got three clear, distinct components. The part one, which is the thing that came out as a result of reference beam, and it is shown in this direction, or sorry, reconstruction beam is shown in that direction. The information carried on it is very, I'm not going to use the word complex, but I'm going to use the word complicated. It's got squares of the original signal plus this value, which may be constant, but squaring of the original information signal is some kind of a distortion or crosstalk, or it's some kind of a noise. You cannot see it. I'll show you a picture of it. But the second part is very important. Twice tau C0 R0. These are the amplified gain times E. What was E? E was the original wavefront, and you have just reconstructed it. It's there. So you can see the object as it was, including both phase and amplitude. And then finally, the third part here, you will see it's got some angle, which is twice the angle of the reference beam, and is going in this direction 3. And that is carrying an information which is the complex conjugate of the original wavefront. Now, what does that mean? It means all the phases in that are inverted. Now let's look at some demo of these terms and interpret. I'm going to call this interpretation of these three terms. And particularly, what does the conjugate, complex conjugate means? The first, the DC part or the noise part, which is simply, if you look at it with your eyes, look at it in this direction, as shown in the diagram, looking directly onto the reconstruction wave direction, you will see something that you cannot tell anything out of. It's like this picture here. Now, if you put your eyes directly in front of the hologram the same way that original object was located, you will see original object reconstructed, including phase and amplitude. So this diagram of a pendant here shows the eye, which was my original object, with pupil bulging out and eyelashes sticking out. Very similar to the original one. In fact, if you have it in hand, if you tried it, one of those pendants you can buy from the market, you can do this experiment. And now the third part is the one that I've been calling funny. If you put your eyes where this diagram is shown, and you will see the reconstructed image of the original one, but indeed I made this picture from a hologram. And look at it, for example, the pupil of the eye that is concave, and the eyelashes are sticking in instead of sticking out. This is because of the phase inversion. And so you will get this, I call that funny image, but it's really mathematically complex conjugate. So this shows mathematically it works. Now I want to make sure that the word conjugate image I use the word conjugate image and principal image to differentiate from the virtual image and real image that we use in imaging optics. This complex complex conjugate, depending on how you make your hologram, could be real or could be a virtual image. So thank you very much for watching this video, and I invite you to look at part 1, which is a little easier, and it's qualitative treatment of the topic. Thanks again. Till next time. This is Secrets of Nature Expedition.